Linear systems. In this lesson, we use Gaussian elimination to solve a system of linear equations. Suppose that we want to find the parabola which passes through the points 0, 2, 1, 1, and 3, 5. In this case, we know x and y and we want to find the unknown coefficients a, b, and c. We can write the problem as a linear system. We want to find the solution which satisfies all three constraints. We can rewrite the system in the usual form by moving the coefficients to the left of the unknowns, and the constants to the right of the equal sign. It should be clear from the previous lesson, that the left-hand side of this linear system may be written as the product of two matrices, a 3 by 3 matrix of coefficients, and a 3 by 1 matrix of unknowns. Before solving this problem, let's consider the solution to a general linear system. Here's a general linear system of equations for n unknowns and m constraints. We can write this system as a matrix equation, using the product of an m by n coefficient matrix, and an n-dimensional vector of unknowns on the left-hand side, and an m-dimensional vector of constants on the right-hand side. We can interpret this equation as a linear operator A, mapping a vector x into the vector b, and we need the vector x, that satisfies the equation ax equals b. One way that we can further simplify the notation of this problem, is to use an augmented matrix. In an augmented matrix, the solution vector x is implicit. Gaussian elimination is an efficient and systematic way to solve a linear system of equations. It consists of two stages. The first stage, called forward elimination, puts a matrix into row echelon form. The second stage, called backward elimination, then puts the new matrix in reduced row echelon form through back substitution. In both stages, we are allowed to use the three elementary row operations. Interchange any two rows, multiply any row by a non-zero scalar, and add any row by a scalar multiple of another row. Let's use Gaussian elimination to find the solution to the augmented matrix we obtained earlier. The first stage is forward elimination. To put the matrix in row echelon form, we start by reducing the first column. Since the first row contains a 0, we will interchange the first row and the second row. We zero out the first element in the third row, by subtracting from the third row, 9 times the first row. The last row is all negatives. We multiply it by -1 to make it all positive. That's better. We can now move to the second column. We interchange the second and third rows. Finally, we divide the second row by 6, so that the second pivot is a 1. The augmented matrix is now in row echelon form, with 3 pivots. During the second stage of Gaussian elimination, we start from the last row and work up using row reduction, to get to reduced row echelon form, in which every element above a pivot is 0. We start with the last pivot. We want to zero out the elements above this pivot. Subtract 4/3 times the third row from the second row. Now subtract the third row from the first row. We can move to the second pivot. To zero out the element above the second pivot, we subtract the second row from the first row. The matrix is now in reduced row echelon form. The solution is A equals 1, B equals -2, and C equals 2. We just solved a linear system with a unique solution. In general, how many solutions can a linear system have? A linear system can have 0, 1, or infinitely many solutions. Consider this linear system. To find the solution we use Gaussian elimination. First, we write the system as an augmented matrix. Now, we perform forward elimination to get the row echelon form. I'll skip the tedious details. After the matrix is in row echelon form, we would typically perform backward elimination to get the matrix into reduced row echelon form. But there is a problem. The bottom row has a pivot on the right-hand side. This row says that 0 equals 2. The system is inconsistent and therefore there are no solutions. Note that the rank of A is 3, but the rank of the augmented matrix is 4. A system only has a solution if the rank of a matrix equals the rank of the augmented matrix. Let's go back to the original system. This time, change the 6 on the right-hand side to a 4. Again, rewrite the system as an augmented matrix. And again, we perform forward elimination to put the matrix in row echelon form. This time we have no pivots on the right-hand side, but as you may have guessed, we still have a row of zeros on the left-hand side. We have a consistent system, so we can now perform backward elimination. This gives us the reduced row echelon form of the matrix. There are a few important features of this matrix to consider. The matrix has 3 pivots, but 4 columns on the left-hand side. The extra column results in a free variable, which in turn gives us a non-unique solution. The pivots on the left-hand side give us the particular solution. The variable associated with the extra column pivots give us the homogeneous or null space solution. It may be easier to see the form of the solution if we explicitly write out the reduced linear system. The system has 3 equations but 4 unknowns. There are insufficient constraints to solve the problem uniquely, so we'll solve the system in terms of x4. This is the same system. Since x4 is free and arbitrary, we'll replace it by a constant c, to avoid confusion. We have that the solution is the sum of 2 vectors, a particular solution, and a homogeneous or null space solution. This means that there are infinitely many solutions. In general, a system has a unique solution if and only if the rank of the matrix A equals the number of rows of A equals the number of columns of A. This means that the number of true unknowns equals the number of equations.